Okay, hello again, everyone. So this is the fabled consecutive day upload. Maybe there'll be another one today. Who knows? So last time for chemistry, we covered quite a bit, which was to do all of it's very important, and it's to do with the type of bonding that chemicals make, why they actually make bonds in the first place, and also I suppose the general gist of the periodic table. Those are the main points that we went through. And for today, what we're going to be looking at is we're going to be looking at the kinds of bonds that the chemicals make a bit more in detail, right? We kind of alluded to intermolecular forces last time. So this time I want to just go into that in a bit more detail. And after that, we can look a bit more into what giant covalent structures are. That's a really interesting and fascinating case study. And the basis that you're going to have here for chemistry will help you understand the deeper molecular structure in life for biology as well. So if you are interested towards the biological sciences, there's something to keep in mind that a lot of the stuff that I'm teaching about right now, this is going to help you later on for understanding what actually underpins the chemical structures in biology, because that is something that we will go through much later on in the future. Okay, so let's start. Okay, now recall that from last time we were talking about two different kinds of forces. We talked about both of it. You can, I guess, capitalize an acronym as IMF, right? But we have intermolecular forces, and we also have intramolecular forces. Okay, so we are right now talking about the forces that's present between matter and that we're talking about like chemicals, I suppose, right? Intermolecular forces are the forces between particles, or you can say between molecules, right? So for example, if I have an oxygen here, another oxygen here, they'll be expressing a weak intermolecular force between each other. There are three different kinds of intermolecular forces, but I'm not going to go into that much detail right now. It is quite interesting though, but I'm just going to leave it at that for the time being, okay? Because we only just need to know this for the moment. And then for the intramolecular forces, those are the forces that are within the molecules. Okay, so for example, in the case of oxygen and oxygen, right, this would be a covalent bond. In the case of a metal, which has metallic bonding, right, it would be, of course, metallic. And in the case of some ions in salt, it would be ionic. Okay, those are the three kinds of intermolecular forces. So right now we're just going to focus a bit more about the role of intermolecular forces in chemistry. And I want to start by just saying that intermolecular forces, these are, again, the forces that are holding that are attracted, well, they're weaker attractions on a relative scale, right? So intermolecular forces are stronger, but intermolecular forces are weaker compared to intramolecular forces. But they still do act. They act within the particles. And this has a big link towards physics as well. As you'll see later, we have different kinds of energies based on this force over here. But what these forces do is they essentially control what the state of matter is. Okay, so they help control the state of matter. And when we're talking about state of matter, we're referring to whether the matter is a solid, liquid, or gas, right? So we're talking about the different phases. Of course, there are more than just solid, liquid, and gases, but we're only going to talk about just those three for the time being. So, just so you know, in terms of the particle model, a typical solid will look like this. Okay, so let's use oxygen as an example. If I froze oxygen, the atoms might arrange like this. And I am going to have to keep copying and pasting this. So here, and here, and here, and here. So that's kind of an example of what the oxygen atoms might look like if they're frozen. Of course, it's a bit more nuanced than that. In reality, there's a slight distribution of charge, so it might form a crystalline structure instead. So, you know, but the main point of this simplistic model is for you to understand that, as you can see, the key point of this model is that the intermolecular forces are the strongest right now. Are the strongest. And the intermolecular space is minimal. And what we can do is we can actually melt this down by providing this energy, and it will now turn into a liquid. So in a liquid, how the particles are going to look like is you just have some oxygen molecules here, some here, some here, some here, some here, here, and so on. Right, so they have got to be closer together. So let me just again copy and paste this just to make it a little bit quicker for myself. Right, so you can see this here and there. So they're a little bit closer, I suppose. You can find places to squeeze them in. Okay, and what would also be happening is that all of these would be settling to the bottom. So I just take this and move all of these down here, for example, right? So the main point is that all of these molecules are settled towards one particular spot because they're pulled down by gravity. And you can see that there's some gaps between them every now and then. Okay, so this over here would be liquid oxygen as an example, right? And one of the properties of this liquid is that compared to a solid which is very orderly, liquids are more so just taking the shape of the container that they're in, and you can see there's still a bit of a chaotic random motion in them. And in this case, the intermolecular forces are medium, and the intermolecular space is also kind of medium. Okay, and of course you can go back from liquid to solid by freezing it. Okay, now if you provide this liquid a bit more energy, that's going to be enough energy to actually break the intermolecular forces between them. Again, in terms of physics, if you think about the energy transfers, what's actually happening over here is if you provide heat energy, then the heat energy will convert into the electric potential energy between the particles, so the particles will space out more. But anyways, that is going to end up looking like this. So again, this is when you boil it. Boiling is different to evaporation. Evaporation can occur at any temperature, but boiling only occurs at a specific temperature. Now we have the molecules that are further apart. Not only are they further apart, they are also moving in random directions. Okay. Now, in most textbooks, what you're going to see is instead of seeing these diatomic molecules, you're instead going to see single particles instead, right? Keep in mind, I could have chosen to draw these as single particles, but it's important for you to understand that in reality, this is actually what it looks like. So it's not just that you have a single ball that's just floating around. That singular ball is actually a diatomic molecule. It's a representation of whatever the molecule is. So the molecule could even be something that's really complicated, like methane, for example. Methane might look something like this. You'd have one here, one here, one here, and then like one there. And so I could duplicate the structure throughout, and that would be what methane gas looks like, for example, right? So this principle applies for every kind of molecule. And again, if you have this gas, right? So the intermolecular force is now the weakest, but the intermolecular spacing is the highest. And what's going to happen is if we cool this down, it is going to undergo condensation back into a liquid. Okay, so this is basically what is the role of intermolecular forces in terms of changing the state of matter of any kind of substance, right? And these states of matter, they happen at specific temperatures, but that temperature can vary depending on the pressure, and we will look more into that like later on when we're studying higher level physics. But there is a link between the exact point of melting and boiling towards temperature as well as pressure, right? So there's things that it depends on, I suppose. Okay, now in chemistry, where this becomes relevant is that we need to mention what the state symbols are in any kind of chemical reaction. So let me just give you an example, and a typical one that I can think of is combustion. Okay, now combustion over here is the burning of something. Okay, it's the chemical process of reacting something in oxygen to burn it, and this is what it might look like. Okay, so you'd have CH4, or rather than CH4, let me pick something that's maybe more solid. So I'm just going to pick carbon, which is a solid, okay? And that is going to react with oxygen in the air, which is a gas. And in this case, that is just going to produce carbon dioxide, which is also a gas, okay? So this is an example of a chemical reaction where we've included these state symbols here, okay? So you can see that this over here is the coke or the carbon or soot from some kind of fossil fuel. Okay, and then this over here is oxygen gas, and this over here is carbon dioxide. Right? So as a chemist, at times, these state symbols are very important. For the chemical reactions, we're going to see the state symbols are not really that important, but it's a good practice to just be aware of them and write them down. Because there are some chemical reactions where knowing the state symbol makes a lot of difference. For example, if you knew that HCl was as a gas, then this would actually be called hydrogen chloride in a gaseous state. But if it was HCl as an aqueous solution, then this would be hydrochloric acid. Okay, so the four state symbols that you need to know about is S for solid, L for liquid, G for gas, and let me just insert over here instead AQ for aqueous and then G for gas. When I was younger, I always used to get confused between these two, so I'm just going to explain to you what the distinction is between them. Okay, so S is just for anything that's a solid, L is for anything that's a liquid. Now, AQ stands for aqueous, which I never really liked as a state symbol. That's a convention that everyone uses, but I never really liked it because it doesn't really explain what's going on. Aqueous is just fancy talk for dissolved in solution. Okay, so for example, if you've got some salt, let's say NaCl, and you put this salt into some water, the salt is obviously going to start to dissolve in the water if you stir it a bit, and that will then turn it into NaCl aqueous. So that's an example of a reaction where something is turning into something else in solution. It's being dissolved in solution. And in chemistry, saying that something is dissolved is just fancy talk for the fact that that substance is now breaking apart and it's bonding stronger with the water that's in solution, or not necessarily the water, whatever it's dissolving it. Okay, but this again stands for aqueous. But really what that means is that it is now in solution, and G is the gas. Okay. Some people don't prefer writing the symbols like this. You could also write it more like this by showing you a chemical reaction. You could write it like this instead if you prefer, as subscripts. But that is like completely up to you. It's just preference. Okay. So I personally prefer writing it like this. But it is up to you how you would wish to write it. The key point is just to be consistent with it. So if you're writing it like this over here, then you shouldn't suddenly write capital G over here. Just be consistent with it. Okay, but those are how state symbols are used in chemistry. So let me just think of another example. You could have a precipitation reaction, for example. Okay, what could be a typical precipitation? Let's go with barium chloride. Okay, so if we have, let's say, barium nitrate, and if this over here is reacting with silver, or rather, let me pick something else. Yes, NaCl. Okay, so this is a salt, which would be aqueous. This is also going to be aqueous. When these two react, also this has to be having two lots here. So let me just explain what's going on. The charge of barium as an ion is 2 plus. And the charge of a nitrate ion that it's bound to is minus. So there's got to be two lots of this in order for it to neutralize the barium. And this anyway makes it aqueous in solution. For Na, since it's in group 1, the charge is +1. And for Cl, since it's in group 7, the charge is -1. So you just need one lot of this and this. We just need to balance them because there's two negatives over here. We've got to put it 2 over here because we expect them to exchange. And that's going to end up looking something like this. So we have BaCl2 here. This is aqueous. And then we have the NaNO3 twice here. Okay, so this over here would now be aqueous as well. But the thing that's special here is that barium chloride forms pretty strong bonds to the point where it solidifies. Okay, so you can see that we have a full solution here. But now it seems like something that solidifies outwards. Okay, so we call this a precipitation reaction. A precipitation reaction is a reaction that leads to the observation of a solid being formed. So it's almost like magic. If you see it for the first time, you mix these two liquids and you suddenly see the solid powder that's forming from the liquid that you're mixing. That looks magical, right? But again, we call it precipitation. That is very similar to the weather word of precipitation. In weather, precipitation means for the rain to coalesce and then fall down, right? So in chemistry, precipitation means for the solid to collect together and then fall down in solution. So it is basically the same thing. But there's a different context for it, right? But that's an example of another case where the state symbols become important in figuring out whether what do you call it? Whether there is a precipitation reaction happening or not. Okay, but that's the only area that's about intermolecular forces. There's not going to be too much else that we'll go into, like the importance of them in chemistry. But the other area that I just wanted to go back on was with ionic structure. So we'll just briefly talk about a dionic ionic structure. So we've already talked about ionic structures from last time, where I've given you examples. For instance, if we have a metal and a nonmetal. In this case, I'm just going to use sodium chloride again to recall that sodium has an electronic configuration of, I believe, 2, 8, and 1. And chlorine has an electronic configuration of 2, 8, and 7. So what's going to happen is this guy is going to give one of the electrons to chlorine, and that's going to end up forming Na ion with 2,8 as the electronic configuration, and then chloride ion with a configuration of 2,8,8. Okay, so what will happen is this Na plus will bond with the Cl minus due to that attractive electrostatic force between the unlike charges. Okay, and it just so turns out that in an ionic structure, what will happen is you're not just going to have one cation here and one anion here. You're going to have a big array of them as a cube, right? So if I had to draw this, it would look more like this. I would have chlorine here. And let me use my copy paste tool to save me again. So that might look something like this. Okay. And imagine this on a bigger kind of scale. Hold on. So I take this, put this here, and then put this here. So you can see you get this beautiful kind of array. It's like a cube. And of course, right now I'm drawing it in 2D, but you can imagine this going backwards in 3D as well. Okay, what I've drawn over here is just a snippet of the giant ionic structure that you would see in any kind of salt. Okay, some salts are a bit more complicated, where you won't exactly see this like cuboid array, but you will still see an array anyways. An array is just a repeating periodic kind of unit, right, that extends out in 3 directions. Okay, now what I want to emphasize for you here is, in a giant ionic structure, this is an example of a solid. And you can see that over here, the structure is not held at all by any intermolecular forces. There are no intermolecular forces here. Everything is held together by intramolecular forces, which is the ionic bond. So it's fully made up of ionic bonds in 3D. Okay, so this extends outwards in 3D. And what that basically means is, if you wanted to melt this, you would have to break down every individual ionic bond that was present, which takes an insane amount of energy. I believe for sodium chloride, for example, if I'm not mistaken, I think like the melting point is like 1,500 degrees Celsius, something around that area. So you can get an idea of how absurd it is in terms of energy levels for you to actually break this down. Compared to water, for example, water can be boiled at 100 degrees Celsius and can be frozen at 0 degrees Celsius. So if you compare 0 degrees Celsius, which is the melting point of water, for this guy over here, which has like melting points in the range of 1,000 degrees, that should give you an idea of how insane, how strong the ionic bonds are, and the fact that you have to break every single ionic bond in order for you to actually, what's the word? Convert this from a solid to a liquid, right? So main point here is that you need large amounts of energy needed to break down the structure. Okay, we call this a giant structure because it extends out in 3D. Okay, otherwise you would call it simple. As far as I'm aware, there are no such things as a simple ionic structure. The closest that we have in chemistry to something that's simple is a simple covalent structure. But this is the main point you need to keep in mind for a giant ionic structure. Apart from that, it's just that if you do melt this, then what's going to end up happening is that in this little box, the particles will end up looking more like this. Right, so they're scattered around. Okay, so I know I've drawn a lot of red in the center for some reason, but it should really just be evenly distributed. Either way, if you melt it, you can see that now the ions are free to flow or free to move around within the container that they're kept in, at least. So they're not like going out of it like a gas would, but they are free to move. And because of this, they could potentially conduct a charge. Okay, so they could conduct a current, which means that they could transfer a charge from one area to another. This will become relevant later on. When we're learning more about electrolysis, for example, that's when it'll become relevant. Okay, now, apart from this, you should also know about, like we were discussing earlier, what a simple covalent structure is. And that is basically when you have just, for instance, a molecule of H2O, which, or even the oxygen that I've drawn earlier, right? That would just be looking like this, like a kind of Mickey Mouse symbol, right? That's upside down. So that's what water looks like. The big one is oxygen, and the two tiny ones are just hydrogen. And if I had a bunch of them together, they would just look something like this. Of course, I'd need to orient them in different directions, but I'm just being a bit lazy copying and pasting them. Okay, so in reality, they would be a bit oriented out. So this over here would be maybe what a gas of H2O looks like under like a high amount of pressure, right? If it was a liquid, then all the molecules would be a bit closer together, and there'd be a bunch of bumps here and there, like of air pockets, right? But otherwise, this is what the simple covalent structure of it would look like. And what's important for you to just understand is that in this case, whether it's a solid, liquid, or gas, depends on the intermolecular forces. So these red lines are the intermolecular forces. Okay, whereas the molecules themselves are held together by intramolecular forces of the covalent bonds. So another point as well is, hopefully you can spot that this one water molecule here is capable of forming like a bunch of intermolecular forces based on the number of particles in that like structure, right? So if you have something that's a bit more complicated, let's say that we have butane, for example, which looks like this. And if I had to draw that structure for you, it would look more like this. So I'd have carbon, 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 and carbon. And then I would have a hydrogen here, 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 another hydrogen here and here, another hydrogen here and here, another one here, here, and here. Okay, so if I have butane, for example, like one here, one here, one here, one here, and one here, hopefully you can appreciate the fact that for one butane molecule, it's able to now have a higher surface area, which now increases the number of intermolecular forces that it can actually form. Okay, the key summary that you should take away from this is that if you have a simple covalent structure of or a molecule that is covalent, and you are increasing the size of that molecule, the longer the chain, the more surface area for which there's going to be more stronger intermolecular forces, right? That's to say, if the structure has a very long chain, you can be more confident that it's going to be a solid. If it has a smaller, like a medium chain, then it could be a liquid. And if it's very small, then it probably will be a gas. Okay, so that's one of the features that affects whether it's going to be a solid, liquid, or gas. So key point is that longer chains have more surface area for forming intermolecular forces. So longer chains are likelier to be solids and liquids. Okay, so that again is an example with butane. So you can expect that if I added another carbon in there for a molecule like pentane, then that might tend towards a solid. But I believe it's only until the 11th carbon or the 12th carbon that it becomes a solid. I think before that it stays as a liquid at room temperature at least. Okay, and keep in mind that all of these forces are due to the intermolecular, are due to the electrostatic forces between the particles, right? Another key point here is if you contrast this to the ionic structure that we had earlier, these guys do not conduct a charge because they are not ions. They are just compounds of atoms that are bonded together, right? So they're not ions. So they do not conduct any charge. That is why, for example, if you have water and you expose that water to electricity, water actually does not conduct a charge, but it does conduct a charge if there are any solutes like sodium and chloride that are dissolved in the water. Because that sodium chloride that's dissolved in the water would be an ion that's free to move around and actually transfer the charge. So the reason why people might get electrocuted when they are wet in their hands and they might be touching a socket, the reason why that electrocution happens is because of the ions that are in that dirty water. But if you theoretically had distilled water, then that wouldn't be able to transmit any kind of charge. It's just that, on our hands, there's a lot of ions present. So if we do put any water on our hand, it's going to suck up those ions, and that's going to cause us to get electrocuted. And if it's not on our hand, then it might be in the socket instead. Another thing as well is to consider is just the voltage, because if the voltage is high enough, it will just ionize the water. So it gets a bit complicated. Okay, but this is just the background of a simple covalent structure that you should be aware of, right? So the equation that I wrote about up here, for example, which is a combustion equation, these two, oxygen and carbon dioxide, are both simple covalent structures. But this guy over here, which is carbon or coal or coke, this would be more akin to, I suppose, a giant covalent structure, which we'll look more into that later on. Okay. So now, just shifting away from that, we're going to look into one more thing before we look at a giant covalent structure, which is what polymers are. Okay, we're not going to go into too much detail. I'm just going to give you like a brief outline of what this word means, because this is a really important word in biology, at least, so you might need it later on, but it really isn't the topic of chemistry. A polymer, so mer stands for molecule, poly means many, so polymer means many molecules bonded together. So a polymer is a group of repeating, that would be a group of repeating monomers joined together in long chains. Okay, and a monomer is when you just have a single repeating unit. So the simplest one I can think of would just be ethene. Ethene looks something like this. Okay, it's a bit more nuanced than this, but this is just a bit of a simplification, okay? So ethene looks like this, and polyethene, if you join many of these together under the right conditions, it will look more like this. So I'm just going to copy this, paste this here, paste this here, paste this here, and so on. And if I have layers of these together, like multiple chains together, that forms basically plastic because of the strong intermolecular forces between the long chains, right? But this is actually one form of plastic, what plastic actually looks like, right? And thus leads to the advantages and disadvantages of plastic. So plastic is very helpful because you can use it in many different situations. It's an insulator as well, and it's pretty rigid for its size, as well as the fact that it's pretty cheap to make that much amount of plastic, and you can sell it for a good amount of value. Okay, that's like the benefit of it. But the downside is that because it has this very long kind of structure, it is a nightmare for decomposers in nature to try and break this out and return it to nature as part of the carbon cycle. So it is a pretty bad environmental pollutant. So you should always just make sure that if you have any plastic, you put it into the right bin bag and you don't just dispose it onto the streets. Okay, but that is the difference between ethene and polyethene. So polyethene is the polymer and the monomer is ethene. Some people call these polythene, okay? Some people call them polyethene. The chemical name for it is actually polyethene, but you know, in typical English, we can call it polythene, or even more so in typical English, we just call it a plastic bag, because that is what it is. It's plastic. You can modify this in different ways, but we will look into that in more detail later on. Okay, but this is just an example of one kind of polymer and monomer, and there's many different kinds out there. The entire premise of polymers and monomers is really important to life. to, as in, it's very important to biology, because a lot of biology, a lot of organisms are made up essentially of polymers. I'm saying a lot. It's not a lot. It's every single organism that we know about is made up of polymers. Okay, so apart from that, just be able to identify the fact that this is one repeating unit of this polyethene here. You could also argue that this is a repeating unit. This is a rare case because ethene is symmetrical, where you could argue that, but that's not always going to be the case if this was like a different molecule. Right, so then from that, we'll just move on to a giant covalent structure, which is probably one of the more interesting areas. Okay, so remember, giant just means it extends in 3D, and covalent means you have covalent bonds that go out in every direction. Typically speaking, covalent bonds tend to be stronger than ionic bonds. Like, it's easier to separate ionic bonds than it is covalent bonds, thus leading to things like diamond, for example. So that's a bit of a spoiler, I suppose. But let me just first explain like one of the most famous compounds that can form a variety of different kinds of structures is carbon. In chemistry, we call this allotropy. Okay, and allotrope is alternate versions. So it's alternate versions of elements expressing it themselves. So for example, for carbon, right now in this section, we're going to just look fully into carbon, just so you can get an idea of what the giant covalent structure looks like. But just so you're aware, in real life, typically every mineral and every like gemstone is made up of a combination of being a giant covalent structure, as well as in some cases partly ionic. Okay, so it extends and it's usually like an array that makes a crystal. So if you ever see something that looks like a crystal, like a pretty crystal, that is on a microscopic level, you know, with the atomic on the atomic level, that is a periodic kind of structure that repeats, and you will see this for diamond. Okay, but anyways, the first allotrope of carbon that we're going to talk about is graphite, and we'll start with graphene first. Okay, so carbon, remember that from what we discussed last time, carbon is in that sweet middle Goldilocks region where it's like the halfway point between one noble gas and another noble gas in terms of the electronic configuration. And that leads to carbon basically being semi-stable, so it's able to form a lot of different structures. And that's also the reason why we are carbon-based life forms. It's because of the fact that carbon is very versatile in that regard. The other candidate would be silicon, but silicon is too bulky and therefore forms what do you call it? It's not as versatile as carbon because it cannot really form liquids as much. It forms solids more likely. So if there was a, you know, it's a good piece of sci-fi, I suppose. But if there was some kind of alien that was made up of silicon, you would expect them to be very rock-like in appearance, you know. But anyways, graphene has a structure that's quite interesting. It looks like this. Remember that carbon has a electronic configuration of 2 and 4. It wants 4 electrons. So what it's going to do, okay, to get 4 electrons, it's just going to share them in covalent bonds, right? So what you would have in graphene is you would expect there to be a carbon that's bonded to 4 other carbons. But instead, for some reason, the carbons are more so looking like this. They look like a honeycomb. Okay, now all I gotta do is repeat this honeycomb pattern. Okay, so what you basically have is you have this one honeycomb kind of lattice. You can see that in the middle of it, there is exactly 1 carbon with 3 bonds only. And this, by the way, extends outwards to towards 3D in every direction. Okay, so that, again, is what it looks like. So, as you can spot, the carbons are supposed to have 4 bonds, 4 covalent bonds in total. But instead, in this case, they're having 3 covalent bonds maximum. So, to make up for that, what basically happens... Let me just do this one last time. Yep, another spot there. Okay, so to make up for this, what this graphene does is it does a really smart trick where one of the carbons, okay, so every carbon gives up 1 electron. And we call this a delocalized electron that's free to roam around. The lattice. Okay, so you'd have a free electron moving around here, another one here, another one here, and it roams around this kind of lattice here. Okay, so what this actually means is because there are free electrons that are free to move around throughout this graphene layer, it's actually a rare case where you have a covalent structure. But despite that, it can actually conduct electricity and heat. Which is why graphene tends to be used for conducting electricity. We can use these long kind of rods that are made up of multiple layers of graphene. But once we have these in layers like this, okay, so if you look at this layer, it's quite difficult to cut the layer this way. But what you can do is you can actually, on a 3D kind of scale, if there was another layer above it, you can cut right in the middle between them, okay? And that would look something like this. So if I drew like a cross section of the layer, like in this kind of direction instead, it would look like this. So I'm just like orienting it from here to here instead, right? So my hand's the graphene layer. It's now looking like this, okay? So this is one layer of graphene. If I have many of these layers all stacked upon each other like this, now we form a structure that's called graphite. Graphite is the exact same chemical that we use in pencils, right? So in pencil lead, we call it lead because a long time ago we used to use lead in them, but we don't use lead anymore. We just use graphite. So in pencil lead, that's actually made up of graphite. And as you can see, I've told you over here that graphene is very hard to break. But graphite, on the other hand, is kind of a mix because the bonds between the layers in graphite are actually weaker intermolecular forces. They're not covalent. Okay, so these guys here are weaker intermolecular forces. Whereas over here, these are all covalent bonds. So if you had to summarize this, the carbon atoms in graphene consist of being bonded to 3 other carbons through covalent bonds. And then for the remaining missing bond, they give up a free electron. And that electron is a delocalized electron that's free to move around the entire structure. And that presence of electrons makes graphene excellent as a conductor of electricity as well as heat. Now, graphite is the same thing, but you have the layers stacked upon each other, okay? So that leads to graphite having a very slimy kind of feel and a flaky feel. That it's very easy to break these layers apart because it's a weaker intermolecular forces between them. And that actually is how pencil lead works, right? So it has a slimy, flaky kind of texture to it. Okay, and again, it is good to be used as an electrode, which is just a rod that can be used to conduct electricity. Okay, so these are some of the forms of carbon. There is one more, which is a fullerene. A fullerene, really, it's a modified version of a graphene ring that is, yeah, so it's a graphene that's kind of molded or folded onto itself like a ring. So that can, so imagine this structure, but imagine it in 3D folding back onto itself, okay? So you could have fullerenes of carbon that are cylinders like this. You could also have fullerenes that are like buckyballs, right? So I can't really draw that well, but imagine like a soccer ball kind of pattern, you know, or a football kind of pattern, which depending on which side of the globe you're on, right? But the main point is that it's that honeycomb pentagon kind of structure on football, okay? That is literally what these carbons can look like in fullerenes. Now, these, because they have delocalized electrons, they can also form, they can also be conductors. And in some cases, the fullerene kind of ball is actually used to hold a molecule. So it can also be used in drug delivery. So if you're trying to give a specific kind of medication to a patient, you could make the patient take the fullerenes, which carries the medication in them. You know, so it is also in some cases used in cancer treatment as well. But I think that's still like an experimental area that they're working on. But these are fullerenes. This guy over here is particularly important. We call this a carbon nanotube. So you might have heard of carbon nanotubes, carbon nanofibers, things like that. This is what it's made up of, right? From what I remember, I believe that carbon nanotubes are still not as strong as spider string, which is what spiders make. If you are comparing them both like on a strength per mass, strength per unit mass kind of comparison. I think spider silk is still stronger, but that's not really surprising because spider silk is also made up of carbon. It's just another polymer of carbon. Okay, now that just covers fullerenes. There's not too much you need to know about it, just apart from this. And they form really interesting compounds. Like, I recommend you just look it up. You can look up on Google Images. There's so many pictures out there of different kinds of fullerenes. You can have fullerenes that are having 60 carbon atoms in them, some with 70, and so on. There are like crazy numbers that have been artificially synthesized. Okay, but that covers the fullerenes. This guy over here, by the way, is called a Buckminster fullerene. Or we call it a buckyball. Okay, so that covers fullerenes, and then moving on from that, we then have what I think is the most interesting, which is diamond. Diamond has a crystalline structure because it is periodic in how it is arranged. Okay, the carbon in diamond follows a structure that we call tetrahedral. Okay, which looks like this. And now, if I had to draw this in 3D, it might look something like this. Okay, where that's kind of like coming outwards like this. Okay, and then like that. And like that on the same plane. So you can imagine this being in 3D. Okay. What I'm going to do is I'm just going to draw a simplified diagram of it like this. So all of these are carbon atoms. Okay. And just to show you what that would look like. It's basically something like this. You'd have one here. You'd have one here. One here. Look at how neatly that fits into each other. It's so beautiful. We'd have one here. Or rather, one here. Another one here. So just from that one repeating unit, look at the kind of structure that we're forming. Can you spot that periodic kind of structure? It's so pretty. Yeah, so probably you can find images of this online as well. But this is typically what the structure looks like, and it's extended out in 3D. And that's actually what diamond's made up of. So the reason why they say that diamond is one of the hardest materials on the planet is because of the sheer amount of covalent bonds that are present in it. Okay? Because of this, it is actually impossible to make a liquid diamond, because the moment you provide enough heat, all of the covalent bonds will instantly dissipate together, and the entire thing gets atomized into a gas instead, right? So diamond actually has no liquid. So it only has a solid form, and then it sublimes. So if you have a piece of diamond, and you have like a blowtorch, and you just supply enough heat energy to that particular diamond, that diamond will, just fade away as a gas. You're not going to see any kind of liquid. It will fade away as a gas of carbon. And then that gas of carbon, because of the high temperature, will immediately burn in the air and react with oxygen. So that will just turn into this kind of carbon dioxide. Okay, but otherwise on its own, it's very inert. Okay, and it is an insulator because it has no free electrons at all, right? So really, diamond consists of a lattice of carbon having 4 covalent bonds. And what happens is the periodic pattern extends in 3D. And the reason why it's so tough is because rather than being bonded by intermolecular forces, it's bonded by stronger intramolecular forces of covalent bonds. So it's bonded by covalent bonds. So when you're trying to heat it up, you're not getting rid of the weaker intermolecular forces. You are trying to get rid of the intramolecular forces, which require way more energy for you to get rid of. Okay, and that's the telling feature of diamond. One more point as well is that this structure here has a name. We call this a tetrahedral structure. It's because it's supposed to represent the vertices of the tetrahedral kind of like prism. So you can imagine one triangle here, another triangle here, another triangle down here. That is the tetrahedral structure, and this kind of carbon is actually in the center of the pyramid, right? But that is a what it looks like. So we call this a tetrahedral lattice. And that's not the only thing that has like a tetrahedral lattice. For example, you can also look at quartz. Quartz crystals is actually a giant covalent structure of silicon dioxide. So you have SiO2 that repeats throughout it. It's the same exact structure, but basically wherever you see these lines over here, there's an oxygen in the middle. So imagine the same structure, but with an O atom in the middle of these lines, and then silicon at these centers here. Okay, so that is actually what quartz looks like. And quartz is not as hard as diamond, because silicon dioxide has a weaker bond compared to carbon oxide, I suppose. Right, but that again is the key feature of diamond here. Right, so you can call the silicon dioxide quartz, or you can also call them silica as well. Okay, but yeah, so if you ever wanted to draw this, you would have to draw this kind of tetrahedral structure, and just basically copy and paste this until you see something that repeats as a pattern. Okay, so we're just going to cover a brief point, which is just to do with the applications of what we discuss here, but in terms of nanotechnology. Okay, so talking about nanotech, okay, a very interesting kind of field. This is when we are using nanoparticles, right? So nanoparticles would count as the fluorines that we discussed earlier. And if you might recall, nano is referring to anything that's on the size of 10 to the power of minus 9 meters. Okay, so that is what nanotechnology is doing. Nanotechnology is looking at the use of nanoparticles, of which, for example, fluorines count. Okay, so for instance, like I discussed earlier, you could use fluorines to treat cancer potentially. You could also use fluorines to deliver certain kinds of chemicals, and you could also use fluorines to conduct electricity, right? Just so you're aware of it as well, for nanoparticles, there we have a scale for this, where fine particles, which we call PM 2.5, these have diameters that are in the range of 100 to 2500 nanometers. Okay, so again, remember that this is 10 to the power of minus 9. So if I had to convert 2500 nanometers into meters, that would just be 2.5 times 10 to the power of minus 7. Up, is that right? Yeah, 1. So that would be 1, 2, 3. Oh, no, that would be 6 meters. Okay, so these over here would be fine particles. And then you could also have coarse particles. And coarse particles are classified as PM10. Okay, and these would have diameters that are between 1 times 10 to the power of minus 5 meters. And it varies, I suppose, to a larger number. So that would be 2.5 times 10 to the minus 6 meters, right? So that's 2.5 micrometers. Okay, and the more common name for coarse particles as well is this dust. So when we are talking about nanotech, we're talking about particles that are way finer than dust. Okay, of course, if you have dust particles that are that fine, that could be bad for the body, because if you breathe it in, it could cause harm to the respiratory system. But the key reason why this is important to mention is because it relates back to surface area to volume ratio, which we discovered which we talked about in biology, right? So remember that surface area to volume ratio, right? This again is just the surface area to the volume of a substance. And the key point here is nanotech has a higher surface area to volume ratio. So if you have a substance and you're trying to distribute it quicker, maybe you're trying to increase the rate of diffusion, then using a fine particle might be better than a coarse particle, right? That's the key point here. So just to give you an example, right? If I have a cube of a nanoparticle, okay, and let's Let's just, for simplification, just to illustrate the point, let's say that this was a cube that was 1 meters in length. Okay, in that case, if you wanted to find the SAVR of this cube, that would be 6 times 1 squared, because the surface area of one face is 1 squared. So 6 times 1 squared divided by the volume, which is 1 cubed, would be 6. This is the surface area to volume ratio of a cube. Now, if we take the same cube, but we just make it smaller, so we scale it down. So what you can see would happen is, now we can have this 1 nanometer here, 1 nanometer here, 1 nanometer here, and we're going to get the same exact calculation. But this time it's going to be in units of 6 per Newton, 6 per nanometer, which if you converted it to per meter to compare it, would actually be 6 times 10 to the power of 9 meters, meaning the surface area to volume ratio has increased by a factor of 9. Well, I say factor of 9, should be factor of 10 to the power of 9 increased. Okay, that is to say that if you are trying to use a substance to increase the rate of diffusion, etc., then using nanotechnology might just be the way to go. This becomes really important in biology, for example, right? It's the reason why, if you're eating any food, you'd want to chew on it beforehand, okay? And in terms of chemistry, this doesn't have applications just in biology. You might also want to use this in industrial applications, okay? We haven't discussed this yet, but I'll just bring it up right now. In chemistry, we have a substance that's called a catalyst, or different substances that are called catalysts. Catalysts, just for the time being, what they do is they basically speed up the reaction without taking part in it. Or, I guess you could say, they speed up the reaction without being used up. So they speed up reaction without being used up. We'll look into them into a bit more detail later. But my point is, if you have a catalyst with a higher surface area to volume ratio, it's only then that it becomes more effective. Meaning, for industrial applications, if you have a fluid and you are throwing in some solid catalyst into that, throwing in a big brick of a solid catalyst is a pretty bad idea. Okay, if you want to make that industrial process more effective, then what you should be doing instead is you throw a bag that's containing this nanoparticle kind of fine powder that you toss into there. Okay, and you want to make sure that you don't breathe in that stuff, because that is going to harm your respiratory system. Okay, but you throw this kind of fine particles into that mixer, and then later on you separate it from the liquid. But that would increase the rate of reaction exponentially as compared to it being like a brick, for example, right? So in this case, this would be a brick, and this would just be, a fine particle. So again, having a surface area to volume ratio of this much would increase the rate of reaction by this factor. So that is the reason why we're mentioning it right now. Okay, but remember that the main drawback of them is just the fact that trying to manufacture them might take a lot of time, and there's also the fact that they can pose a harm to the environment if they escape to the environment, right? People who breathe them in can have a pretty bad time with what do you call it? With the respiratory system, because they can get stuck in the lining of the cilia and so on, and that can be a nightmare for the cells of the body. Okay. But otherwise, this summarizes basically what we are doing for this particular session. Okay, so for the next session, we will look a bit more about numbers in chemistry. So people who don't like maths, you might not like the next session as much, but if you are interested in doing further chemistry, then it is something that you just need to be aware of. And we call it quantitative chemistry. So that's what we'll be looking at, into like just the basics of it at least, because that's how chemists actually measure the right proportions of chemical reactions or the right materials needed for a chemical reaction to occur. Okay, but again, just to summarize, right? So remember that intermolecular forces are opposed to intramolecular forces. They're both different things. Intramolecular forces are the bonds within the chemicals, but intermolecular forces are the bonds that are between different chemicals, right? So we've got ones that are within the molecules, and we've got ones that are between the molecules. Okay, so when we're talking about solid, liquids, and gases for simple covalent structures, those are controlled by intermolecular forces. And then that leads to state symbols as well, where you've got solids, liquids, and gases. Most importantly is for you to understand that AQ represents something that's been dissolved. We then talk about a giant ionic structure. The key difference between a giant ionic structure to a simple covalent structure is that the solid, liquid, gas properties of a giant ionic structure is controlled by intermolecular forces rather than intramolecular or sorry, the other way around. So in a giant ionic lattice, it's controlled by intramolecular forces rather than intramolecular forces. That is to say that in a giant ionic lattice, it's controlled by ionic bonds rather than the intermolecular forces. So intermolecular forces are very weak, but in a giant ionic lattice, it's held together by ionic bonds, which is why that metals, or rather salts like sodium chloride, are very hard to melt. It's way easier to dissolve, but it's a lot harder to actually melt. And then we talked about a simple covalent structure, of which you should recall that polymers, they are kind of in the boundary between a giant covalent structure and a simple covalent structure, but they're made up of many repeating units of these monomers that are joined together, and that causes them to have a higher surface area to form more intermolecular forces to form a stronger kind of solid structure rather than a liquid or a gas. And then we talk about giant covalent structures, of which there are many in nature, like ruby, emerald, sapphire, so on. These are all mixtures of covalent and ionic, but the one that we talked about is the allotropes of carbon, of which we can see graphene, which is a conductor of electricity, graphite, which has these layers over here, and then fullerenes, which have these carbon nanotubes or these buckyballs, basically, right? And then the most interesting of them, I think, is this diamond, where you can see this periodic kind of structure that repeats around in 3D. And that leads to diamond having that very beautiful crystal-like structure. And then apart from that, we also talked about nanotechnology being useful in chemistry as well as in biology, right? So in biology, it could be used for some kind of drug delivery, perhaps, right? Or a more efficient kind of diffusion rate. Maybe there's something along those lines for biology. But in chemistry, it could be used as a catalyst to make the actual reaction speed up a bit higher, right? So if you do have any kind of catalyst, that catalyst is going to be more effective if you are using um, nanoscopic particles of that catalyst rather than bigger scaled particles of the catalyst. Okay. Right, so that covers it then for that particular lecture. So I hope you enjoyed. If you do have any feedback on it, please do let me know in the comments. If there's another topic you want me to cover, or if you have any criticism that could help me improve, please do let me know. If you did enjoy the lecture, please feel free to support me on Patreon as well. And again, for next time, we'll be continuing with quantitative chemistry for chemistry. And the next video that I release will be about physics, and we'll continue with that rotation like that. All right, see you next time then.